Let's take a look at stars off the main sequence and stellar parallax. So last time we looked at the HR diagram, and I pointed out that most of the stars that we observe are along the main sequence, which lies here on an HR diagram. But not all stars are on the main sequence, and let's consider those stars that are not on the main sequence. So for example, some stars that we observe are here in the lower left corner of the HR diagram. And let's think about what those stars are like. Well, they have a very high temperature and they have a relatively low luminosity. And if we think about the luminosity equation, luminosity is sigma A T to the fourth, if the temperature is relatively high but the luminosity is low, that indicates that the surface area has to be relatively small, which means that it has to be a physically small star. These stars are called white dwarfs. White because they have a high surface temperature and so they appear the color white, and dwarfs because they're physically small stars. Now, some other stars are found in this part of the HR diagram, above the main sequence and over to the right. Some stars are even higher up on the HR diagram. These stars in this section have a relatively low surface temperature, but a relatively large luminosity. Again, if we look at the luminosity equation, if it has a high luminosity but a low temperature, that indicates that we have to have a high surface area, which means that these are physically large stars. These are called the red giant stars, and the ones that are even further up have an even larger luminosity, and so they have to be even larger physically. These are called supergiant stars. And then the last part of the HR diagram that we're going to look at is a strip of stars right here. This is called the instability strip. Now, we're not going to go too far into detail about this, but what you need to know is that stars in this region of the HR diagram are not completely stable. They pulsate. And due to internal processes within the star, they expand and they contract. Their radius actually changes, and their surface temperature changes, which means that their luminosity changes. It oscillates over time. And again, we're not going to go into too much detail about that. You just need to know that in this area of the HR diagram, we have unstable stars with oscillating luminosities. Now, in order to explain what white dwarfs are and red giant stars are and red supergiant stars are, we have to think about the evolution of stars once they leave the main sequence. So we're going to do that, and we'll think about a low mass star, a medium mass star, and a high mass star. A low mass star, remember, has a relatively low surface temperature, so it appears red. It has a relatively low luminosity, and it has a low fusion rate. So it takes it a very long time for it to use up its hydrogen fuel. The high mass star has a relatively high surface temperature, so it appears bluish-white. It has a very high luminosity, and it has a very high rate of fusion, so it will use up its hydrogen fuel in its core very rapidly. And then the medium mass star is somewhere between them. So let's think about that low mass star. Eventually, after a very long time, it will use up the hydrogen in its core, and it will no longer be able to have any hydrogen fusion in its core. Once that happens, there's no more outward radiation pressure, and there's only gravitational force inward. Hydrostatic equilibrium is disrupted. And so the core of the star begins to collapse, and the core of the star increases in temperature and pressure until it's actually able to fuse helium. Now, I'm going to give a very abbreviated story of what happens here, but once it starts to fuse helium, it actually begins to expand in the outer part of the star. The outer part of the star becomes physically larger. The radius of the star increases by a great deal. But the surface temperature of the star decreases. But the radius becomes so much larger that the luminosity actually increases. So what we get is a high radius, a high luminosity, and a low temperature. This is a red giant. The red giants that we saw in the HR diagram, this is where they come from. It's when the star uses up the hydrogen in its core and the outer part of the star expands. Now, eventually, the star becomes unstable, and this can look different for different stars, but eventually what happens is the outer part of the star is blown away by radiation pressure. And when this happens, the outer part of the star is removed and all that's left is the core of the star, and it's exposed. And that exposed core of the star is very, very hot, But that's not fusion that's providing the thermal energy. It's just leftover thermal energy from having been so hot being in the core of the star. So this is a very hot but very small object, about the size of the Earth, but much higher in mass, anywhere between a tenth of a solar mass to a little bit over a solar mass. Medium mass stars also take this route. So, for example, our sun will eventually do what I just described. It will run out of the hydrogen fuel in the core, it will become a red giant. Eventually, the outer part of the sun will be blown away, and all that will be left is the exposed core of the sun, which we will call a white dwarf. For high-mass stars, it's quite different. High-mass stars, they will use up the hydrogen in their core, and the core will collapse, and in this case, it will become what we call a supergiant. But then it will use up the helium fuel, and after that, it will fuse higher and higher elements. So it will eventually fuse elements all the way up to iron. However, if you try to fuse iron, you will not release energy. If you look at the binding energy per nucleon curve, iron is very, very stable. And if you fuse two irons together, you will not get a more stable element out of it. You will not emit energy. You will actually absorb energy when that happens. So at this point, there is no way for fusion to support the star. And the star's core will collapse, and the outer part of the star will fall in upon it, and the star will explode, leaving behind some kind of stellar remnant, which we either call a neutron star, or, if the star is large enough and the explosion is large enough, a black hole. If you'd like to know more about this, I've gone very rapidly through this, but I can link to another video that I made for the older curriculum, which explains this in a little more detail. But let's think about what this would look like on an HR diagram. So imagine we consider the sun. It's on the main sequence, and it spends most of its life on the main sequence, burning hydrogen in its core. But eventually, when it runs out of hydrogen in its core, it will become a red giant. And on the HR diagram, that means it drifts over to here. Now, it spends a little bit of time as a red giant, burning different types of fuel in its core, but eventually the outer layer is blown off, and that's actually called a planetary nebula. We're not going to worry about that. But once that outer part of the star is removed, it will move over to another part of the HR diagram down here, and that leftover core is what we call a white dwarf. For higher mass stars, it looks a little bit different. In a higher mass star, if it's on the main sequence, it would be up here. And it will eventually run out of hydrogen in its core, and it will become what we call a supergiant in this part of the HR diagram. But for these high mass stars, remember, it ends in a core collapse and an explosion, so they don't drift to anywhere else in the HR diagram, they just cease to exist. Now let's take a step back and think about, how do we know the distance to stars? For example, if you see a star in the sky, how do you know if it's a near star that has a low luminosity or a very distant star that has a high luminosity? I mean, if we think about it, the brightness is equal to the luminosity over 4 pi d squared. What we observe from Earth is the brightness. We don't directly observe the luminosity. What we observe from Earth is brightness. So in order to know the luminosity, we have to know the distance. Or in order to know the distance, we have to know the luminosity. And you might think, well, we could get the luminosity. Luminosity is equal to sigma a t to the fourth. And we can observe the spectrum of the star so we could get the temperature of the star. But we do not know the radius of a star. Just by observing a star, we cannot know the radius of it. So that's not a method that can allow us to get the luminosity. Instead, what we have to do is we have to figure out the distance to the star and then determine the luminosity. And the most direct method we have for determining the distance to a star is called stellar parallax. And this is how stellar parallax works. Imagine that here's the sun, and here's the Earth's orbit. And we're going to put a star that we observe right here. Let's think of it as a nearby star. And then there's faraway stars, and I'm going to draw them over on this side. Now, if we have the Earth right here at one time, and an observer observes this nearby star, when they observe the star, it will appear next to this star. Call this star star X. And then we wait 6 months, and the Earth is on the other side of the sun, and we observe this nearby star again. From the perspective of the person on the Earth now, that nearby star is going to be next to this other star, call it star Y. So if we observe the same star 6 months apart, if it's near enough to us, it will appear to move. Remember, at this point, it appears in the sky next to star X. At this point, 6 months later, it appears in the sky next to star Y. This phenomenon is called parallax, and I'm going to define a couple of things in this diagram. Here, this is the distance from the sun to the star, and it's approximately the distance from the Earth to the star as well. This right here is the distance between the Earth and the sun. And the average distance between the Earth and the sun is called an AU, an astronomical unit. It's about 1.50 times 10 to the 11 meters, which is given in your data booklet. And then here there's an angle. And this angle right here, we're going to define as the parallax angle. Now notice, if I had a greater distance, if the nearby star was further away, the parallax angle would be smaller. So the distance to the star is at least roughly inversely proportional to the parallax angle. Now, if you do the geometry, it's not exactly proportional, but it's pretty darn close. So what we end up with is this equation. The distance to the nearby star is equal to 1 over the parallax angle. However, there's some pretty important caveats in that. The distance to the star here, if we use this equation, has to be in parsecs. More about the parsec in a moment. The parallax angle has to be measured in something called an arcsecond. And an arcsecond is a very small unit of angle. It's 1/3600th of a degree. And if you're asking why we would use such a strange angle measurement, well, it has historical reasons. But back to the parsec. The parsec is defined so that an object is 1 parsec away if it has a parallax angle equal to 1 arcsecond. And it turns out that if we do that, the parsec is equal to 3.24 light years. That's given in your data booklet. So this method works very well for earthbound astronomers, out to about 100 parsecs. After that, the parallax angle is too small due to atmospheric effects to be measured accurately. If we send up a satellite to do this, satellites can measure parallax angles out to about 1,000 parsecs, depending on the precision of the instruments on the satellite. Now, the last thing I want to look at is on the HR diagram, we can draw lines of constant radius, and I'll show you what I mean. So here's our HR diagram, here's the main sequence. It turns out that lines approximately like this have constant radius stars on them. So we would have relatively small radius right here, larger radius, and even larger radius up there. And now here at the end, I want to kind of summarize some of the things that astronomers can do when they observe stars. So when astronomers observe a star, they get light from the star, so they can observe the spectrum. From the spectrum, remember, you can look at the spectral lines and you can determine the composition. Pretty impressive. From the spectrum, you can also use Wien's law to estimate the surface temperature of the star. And if you observe those emission and absorption lines, and you compare them to the emission and absorption wavelengths of a stationary source in a laboratory, you can figure out the Doppler shift of the star. And so you can determine the radial velocity of the star toward or away from you. Now, we just talked about parallax, so you could observe the parallax of a star, and if that's possible, you can estimate the distance to the star. There are other distance methods that astronomers use, and they're all very clever, but just know that the parallax method is one of those methods that they can use. And so astronomers can also observe the brightness of the star, and if you observe the brightness of the star and you observe the parallax angle of the star so you know the distance, well, if you know brightness and distance, you can get the luminosity of the star. And if you know the luminosity of the star and you know the temperature of the star from Wien's law and observations of that, you can get the radius of the star using this equation. So you can determine a lot of the physical characteristics of a star just by observing the light from it. And really, this is only scratching the surface of what astronomers are capable of.